Hello, good day. Yeah, in this class, essentially we're going to look at proof by induction. Now, it sometimes happens that a result is found by some means which does not provide the proof. So by mathematical induction, we are going to try to derive some formula which we might not necessarily provide the proof for it. Now, first and foremost, let's, for example, let's consider the following table. So assuming we have n, and the n is an integers that ranges from 1, let's say we have a 1, 2, 3, 4, 5. These are positive integers. So now let's look for the sum of n, sum of the integers up to n. Sum of the integers up to n. So what we're saying here is 1 plus 2. We have 3 plus 3, we have 6 plus 4, we have 10, and 10 plus 5, we have a what? 15. This is the sum of the integers up to n. Okay, then assuming we have n cube is telling us that each of the integers raised to power 3. So 1 raised to power 3 will also give us 1. Here, 2 raised to power 3 means 2 times 2 times 2, and that gives 8. Now 3 raised to power 3, that will give us, that gives 27. Then 4 raised to power 3 is 4 times 4 times 4, and that gives 64. Then 5 raised to power 3 simply means 5 times 5 times 5, and that gives 125. Now, assuming we also want to find the sum of the cubes up to n, sum of the cubes up to n, sum of the cubes of the integers up to n. It simply means here we have 1 plus 8, that gives 9. 9 plus 27, that gives 36. 36 plus 64, that gives 100. 100 plus 125, that gives 225. Then, if you observe carefully, that the sum of the cube here, is the same thing as the square of the fourth row here. The fourth row here is the same thing as the square of the second row. What we are trying to say here is that here we say 1 raised to power 3 plus 2 raised to power 3 plus n raised to power 3 is the same thing. It's the same thing as you were saying 1 plus 2 plus all square. So we are saying that the sum of the cubes up to n is the same thing as the sum of the square of n. So you can see here, you know, you square 1 here, will give you 3 square, 6 square, 10 square, and 15 square give us 225. Then if you look at this, this term here, this term is an arithmetic progression. 1 plus 2 plus 3 up to n is an AP. It's an AP, and whose sum we can find as the sum of this AP. Now, this AP have the first term, the second term, then up to the last term. The last term here is n, and we know that if we have an AP, Sn, the formula is n over 2, open bracket, a plus what? L. Now here, given a is 1 and L is equals to what? N. So that the sum of these, because we are saying the sum of n up to sum of the integral up to n square. So here the sum of the AP will be n over 2 bracket 1 plus n. So if it is natural now, it is natural to say that 1 cube plus 2 cube plus is equals to, in place of this is the sum of, because this one is telling us sum of, so, and the sum will be n over 2 open bracket 1 plus n all square. All what? All square. Now, this proof by induction says that now if the result is true for n, for a number say n, then it is also true for a particular number say n is equals to k. Then if it is true for n is equals to k, that means it is also true for a particular number of n is equals to k plus 1. So this is proof by induction. This is just an introductory part of it, and in our next class we are going to bring out questions and specify the procedure for proof by inductions. And I hope that you enjoyed the class. So here we just look at the introductory part to proof by inductions. And like I said, it's sometimes it happens that we want to find a result, and that result can be found by some means which does not provide a proof. So please, I want to to tell you that by our next class we're going to bring more details on proof by induction. And please do not hesitate, when you come across this video, you can help me subscribe and also share to other platform. Thank you and have a nice time.